Hello viewers, welcome you all. So welcome to the first lecture of these special classes which has been started for the benefit of all those students who are preparing for various competitive exams that are based on physics. Right? It can be UGC, CSIR net, or it can be HP set, or it can be GATE, right? It can be any other university entrance examination, particularly for all those students who are in the undergraduate classes. I mean in the BSc final year, and they are preparing for various entrance examinations of different universities like HPU or PU or other universities in India. So I have started these special classes for the benefit of all these students, right? And in these classes, I am going to cover up some important topics in physics. You know very well that it is very difficult to cover up the entire physics in these classes. So whatever important topics are there, which are usually appear in these examination, questions are asked from these topics. So one by one, I will cover all these topics. In the meantime, if you want that you want to have clarity on particular topic or particular subject in physics, course in physics, I mean like you want to have the clarity in digital electronics or nuclear physics or solid state physics, you can mention the particular topics in the comment box that you want the a lecture, special lecture should be made on that. So now this is the first lecture of this lecture series that I am going to start today, and today I am going to start with with high energy physics or particle physics, right? High energy physics, or I can say particle physics. So all those students who are in the masters, they have already gone through these two courses, high energy physics and particle physics, or nuclear and particle physics, whereas all those students who are in the BSc final, they have just appeared in the BSc final. Now we know very well that in our HPU syllabus, Himachal Pradesh University syllabus, there is choice in BSc final that some colleges are offering nuclear and particle physics, but some are offering other course. So those students who have not studied nuclear and particle physics course in the BSc final, right, they have to put extra efforts. They have to first of all go through the entire course, then after they can understand. Because in this lecture I am going to cover up only the important points of these topics, and then after I will discuss some questions, commonly asked questions from these topics, right? So those students who have already studied these courses, I mean particle physics or high energy physics in MSc, it is beneficial for that. They are on the better side because they have learned all the basic things, right, whether they are in the undergraduate or in the postgraduate. But those who have not gone through it, they have to put extra efforts, right? Now I am coming to this topic, high energy physics or particle physics particularly. So in particle physics, usually in any examination, 3 to 5 questions are asked, right, from this topic, right? Some questions are from the classification of elementary particles, right? Questions can be from the quark model. Questions can be from conservation laws. Question can be from the decay modes of different elementary particles. So but whatever exam you will go, you will see 3 to 5 questions in that exam. If the exam is of 75 to 100 questions, right? And even there can be more questions, but I am saying that 3 to 5 questions are sure, right? So not wasting enough time, Now I'm going further and I'm coming to the main point, that is high energy physics or particle physics. So when we are dealing with the problems of particle physics, first of all we have to remember the classification of elementary particles, right? The first and foremost most thing, that is the classification of elementary particles, right? Now, one important thing that I want to tell you here, that elementary particles are those particles which are building blocks of the entire matter in this universe. These are the particles which are responsible for the different interactions among the mass, among the matter in the universe, right? But there are some fundamental particles which are also part of elementary particles. But fundamental particles are those particles which are fundamental in nature. Fundamental means these particles can be broken down further, and at present we have 12 fundamental particles. So remember, elementary particles and fundamental particles are a bit different thing. Examiner can ask you that he or she can give you options and ask you which of the following is the fundamental particle. So at present the fundamental particle list, as I told you, we have 12 fundamental particles, right? Fundamental particles, right? 12 fundamental particles have 6 leptons. I will tell you what are leptons, plus 6 quarks, right? If you want to go in details for the quark theory, you can refer to my earlier lecture that I have delivered on the quarks model and color confinement, working of the color forces. All these things are mentioned there. So fundamental particles are 6 leptons and 6 quarks, but elementary particles contain all the particles, subatomic particle, which we can't observe with the naked eye. For example, electron, proton, neutron, right? Pi meson, k meson, lambda, sigma, xi, omega, all these are elementary particles, right? And elementary particles have their some properties, right? We can classify them according to their properties, right? So I'm coming to this classification. So we know very well that in the nature there are two type of particles. One are the particle which are responsible for working of forces. We call them as field particles, field operators or field particles. We know very well that we have 4 fundamental forces in nature. So according to that, 4 fundamental particles are there. That is graviton, right? One particle. Then we have a gluon, right? Then we have a photon, right? And ultimately for the last we have a W and a Z bosons, right? So this is for weak interaction, right? This is photon for electromagnetic. Gluon is for a strong or color force. I have explained already, as I told you. And graviton is for a gravitational force. So first of all, we should remember that we have 4 fundamental forces in the nature, and these 4 fundamental forces are electromagnetic force, gravitational force, strong force, and a weak force. And the quanta of these forces or field particle of these forces are represented as this one, right? Now we should also memorize or know the properties of these field particles, right? So if I talk about the photon, right, you can see here it is photon. So what are the properties of photon? Photon is basically a boson particle, right? Now we know very well that what are bosons. Bosons are basically those particles which have either zero or integral spin. So examiner can ask you a very simple question, that whether which of the following particle is boson, which of the following particle is fermion. We know very well that fermions are those particles which have a half integral spin, right? We can classify the particle on the basis of that also. One particles are bosons and other particles are fermions. Remember, all those particles which are bosons, they are field particles. They are responsible for the interaction among different matter, right? Whereas the matter particle, the particle that made up the entire matter in the universe, these particles are fermions, right? and fermions obviously have zero or half integral spin, right? One thing that we should know, that is the comparison between the four fundamental forces. We know very well, as I told you, that we have gravitational force, strong force, electromagnetic force, and weak force. We should know very well that if we take the magnitude of gravitational force as 1, then strong force is 10 raised to power 38 times stronger. Electrostatic force or electromagnetic force is 10 raised to power 36, and it is approximately, weak force is approximately 10 raised to power 15 times. So we should know all these properties also, right? The one more thing that can be asked about the range of these different fundamental forces. We know the range of the gravitational force is infinity. The range of electromagnetic force is also infinity, but the range of strong force is 10 raised to power minus 15 meter, and as far as the range of weak force is concerned, it is around 10 raised to power minus 17 meter. So this is the range, right? And this is the comparison of their strength, right? So we should know, before going into the discussion of high energy physics, first and foremost thing is to know about the fundamental forces and fundamental or and elementary particles. So I think as far as the fundamental forces is concerned, we know that these are the properties of fundamental forces, right? Now, the one thing that examiner can ask you, it can ask you the properties of these different field particles, that is graviton, gluon, or a photon, or W and Z photon. So the properties means the charge of these particles, mass of these particles, right, spin of these particles. So if I talk about the spin, then as I told you that all these particles are bosons. It means they have either zero or integral spin, right? All these particles are bosons, right? So they have either zero or a integral, 1h cut, 2h cut kind of a spin, right? Spin angular momentum, right? So he can ask you that what is the spin of graviton. So we have to remember that the spin of graviton is a 2h cut, right? Or simply 2, right? We should also remember that in high energy physics and particle physics, the units that are used for the measurement of physical quantities, they are different from the conventional SI unit system, right? In high energy physics, we are dealing with very small quantities, very small dimensions, right, of the order of 10 raised to power minus 15 to 10 raised to power minus 30, right? So obviously the units that are used are different. For example, for the measurement of mass, we use the unit AMU, atomic mass unit, right? AMU, right? Similarly, for the measurement of energy, we use the unit mega electron volt or giga electron volt. I have explained all these things in the previous lectures. You can refer to them, right? Now, in high energy physics, it is convenient to take h cut is equal to c is equal to 1. This is called system of natural units. So what we do, we usually express the mass of the elementary particles in terms of either mega electron volt or giga electron volt. Why? Because we know E is equal to mc square, right? So m is equal to E upon c square. It is what? What is it? It is, we are representing the particle in terms of its energy, and when we take c is equal to 1 in the system of natural units, obviously m becomes E. So we represent, you might have seen that the mass of a particle is written as 80 giga electron volt, right? Or it is written as a 0.51 mega electron volt, like that. So it means we are representing the mass in terms of energy. This is a common practice in high energy physics. So examiner can ask you in the multiple choice questions that what is the mass. So we should not confuse that the unit of the mass is kilogram or gram, right? But here the unit used are different, right? So that's why I was saying that the spin of the graviton can be written as 2h cut or simply 2, because we are taking h cut is equal to 1, right? Similarly, we are also taking c is equal to 1, right? So if examiner ask you about the spin, then I told you the spin of the graviton is 2, whereas the spin of other these 3 particles is 1, right? As far as charge is concerned, only these 2 particles, W positive and W negative, they are having positive and negative charge, whereas other particles are neutral, right? As far as the energy, mass of these 4 particles is concerned, we have to remember that the mass of these 4 particles, that is photon, right, graviton, gluon, and a W positive, W negative, W naught, and a Z naught, right? So we know very well that the rest mass of the photon is equal to 0, whereas the rest mass of gluon is also equal to 0, right? Graviton's rest mass is also equal to 0. But as far as the mass of these 4 particles is concerned, W positive has mass approximately 80 giga electron volt. W negative has approximately again 80 giga electron volt, whereas Z has approximately 91 giga electron volt, right? One more particle that is commonly discussed in high energy physics is Higgs boson, right? Higgs boson, right? You will learn about it in the high energy physics course. So Higgs boson is also a boson. So obviously the spin of the particle will be integral, but it has a 0 spin, right? And as far as the mass of this Higgs boson is concerned, it is 112 giga electron volt, right? Its charge is equal to 0. So these are the different properties of these field particles and comparison of the different fundamental forces, right? Now I am coming to the classification of elementary particles, which is very, very important. I told you that I can classify them in 2 categories. The one is field particles and the second is matter particles, right? Matter particles means the particles that made up the entire matter in the universe, right? So matter particle, for matter particle I am going down, taking this, yeah, right. Elementary particle classified into 2 categories. Field particle, I discussed all the properties of field particle. Now I am coming to the matter particles. Matter particles means fermions. I can say these are fermions, right? So in matter particles, I have a one particle are leptons and other particles are baryons, right? So leptons particles and baryons. Now lepton word means light particles, right? The particle which are lighter than the nucleons. So lepton family, I'm not going into the entire details, otherwise it will become very big topic. Leptons contains 6 leptons, I told you, electron, mu, tau, right? Mu positive, tau, right? Then you have a not mu positive, it is mu negative, then tau particle, tau negative, and then you have 3 neutrino associated with them, mu and tau. So we have to remember that this lepton family has 6 particles, electron, muon, and a tau particle, and the 3 neutrino associated with these 3 particles. So this is the family of leptons. Now I am coming to the baryon. Now the baryon family is further divided into 2 groups, right? One is nucleons and other is hyperons. Now what are nucleons? Nucleons means neutron, proton, and their anti-particle, anti-neutron, anti-proton. But the family has 2 members, right? Particle and anti-particles, this concept also be clear in the mind while we are dealing with the high energy physics. Particle and antiparticles are, same kind of thing, but antiparticles have some of the property, inverse to the particle. I can say if the particle has charge positive, then the antiparticle will have charge negative. For example, electron and a positron. This is positron is the antiparticle of electron and vice versa. Spin can be the thing that is opposite in the two particles. So in that case, one particle will have spin clockwise, other will have spin anti-clockwise. So here in nucleon family, I have two particles, neutron and proton. If I come to the hyperons, then hyperon family is further divided into different families. The first one is lambda naught. Lambda naught is the single particle. In this family, it has only one particle. Its antiparticle is lambda naught bar, right? Then we have a next family, sigma, right? Sigma family have a three particles. This is very important. We have to remember the family members of a family, because while calculating the different properties of these elementary particles, it is important to remember that what are the family members of that family. Then the next is xi, right? Xi, we write it xi, so it has two members, right? Xi negative and xi naught, right? So two family members are there. This has three family member, it has one family member, it has two family member, it has six family members. Then omega. Omega is the last particle in this family. It is again a single family member, right? Single particle, right? Now, as far as the antiparticles of these particles, all of them has their corresponding antiparticles, right? So this is the classification of these matter particles and field particles. The one more particle that I didn't mention here, they are mesons, right? Mesons are also bosons, right? So if I want to add them in this classification, I can add them in the classification of a matter, right? Matter particles. But matter particles, can have some bosons, because mesons are again also the particle that has either zero or integral spin, right? So meson family is also very important, because the collection of mesons and baryons, right? Collection of mesons and baryons. This is collectively known as hadrons, right? Hadrons. So mesons have for the different families, that is pi mesons, right? Pi positive, pi negative, pi naught. Three members in this pi meson family. Then we have k mesons, right? K positive, K naught. Two family members are there, and then I have eta mesons. Eta meson is the single family member, right? So this is the family of mesons, right? And they are also bosons, because their spin is integral again, and they are bosons. That's why, right? So we have to remember that what are the families of mesons, different mesons. So in case of pi meson, three family member. In case of k meson, two family members, k positive, k naught. Whereas in eta meson, only one family member, eta naught, right? This is the classification. Now the one thing that I want to tell you here, that here in case of mesons, as we see here, that three different families are present here, 1, 2, 3. So examiner can ask you about the spin or mass or decay mode of these elementary particles in any question. So as far as spin of pi mesons is concerned, right, their spin is equal to 0. As I told you that all these mesons are bosons. Similarly, k meson spin is also equal to 0, and eta meson spin is also equal to 0. But as far as their mass is concerned, now we know very well, we have learned it in Yukawa theory of nuclear forces, that pi mesons, pi positive, pi negative, they have mass approximately equal to 140 mega electron volt, whereas the mass of pi naught is approximately 135 mega electron volt. So we have to remember it, right? If I come to k mesons, k positive, k naught, right, then the mass of k positive is around 493 mega electron volt, whereas the mass of k naught is around 498 mega electron volt. Similarly, the mass of eta naught particle, it is approximately 547 mega electron volt. So we have to remember one thing, that which of these mesons is very massive, heavy. So you can see here eta meson is the heaviest among all these mesons. Now examiner, as I told you, can ask you about the stability, which of the given elementary particle has highest lifetime. For example, he can ask you that what is the lifetime of a neutron. So we know very well that neutron is a stable particle and its lifespan extends from 10 raised to power 32 to even 10 raised to power 34. Some calculation has predicted years, right? So we can say this is a stable particle. Similarly, for electron is again a stable particle, 10 raised to power 28 years. Neutron, right? Neutron has a half-life of around 15 minutes, right? So in this case, examiner can ask you about the, which of the given particles is stable or not stable. He can ask you that what is the antiparticle of, lambda naught. So lambda naught antiparticle is this, right? Similarly, the antiparticle of this is a positive naught. Antiparticle of this is a, right. It doesn't means here that the sigma positive is antiparticle of this. No, it is sigma negative naught. Similarly, xi negative has antiparticle xi negative naught, right? Similarly, xi naught has this antiparticle. Similarly, omega negative antiparticle is omega negative naught, right? So he can ask you about the antiparticles corresponding to a given elementary particle, or he can ask you about the, as I told you, about the spin of the elementary particles also. So we have to also memorize that what is the spin of these elementary particles. Most of the fermions that I discussed here, they have spin half integral, I mean 1 by 2 h cut. But there is one exception, that the spin of this omega negative particle is 3 by 2. So it is usually asked in the examination that what is the spin of omega negative. So it is 3 by 2 h cut. Or I told you what is the spin of graviton. So it is 2 h cut, I told you earlier. So these kind of questions arise from the classification of elementary particles. So this is about the classification of elementary particles and classification of the different fundamental forces in nature and their working. I also told you that what are the fundamental particles. So fundamental particles contains 6 leptons and 6 quarks. I will come to the quarks later on, but 6 leptons, they are covered here, right? You can see. And these fundamental particles are called fundamental because they do not have any substructure. So examiner can ask you, as I told you, that which of the following particle is fundamental. For example, he can give you proton, right? It can be lambda naught, it can be a omega particle, then it can be then given a quark, up quark, right? So you will be asked which of the following is a fundamental. So you have to identify the fundamental particle, right? So these are some basic questions that arise from this entire discussion, right? Now I am coming to the some important properties, or we can say quantum numbers of these elementary particles. Right. We know very well that in atomic physics we come across 4 quantum numbers. But here quantum number means the different parameters, different properties of electron in atomic physics. Here in particle physics, quantum numbers means quantum properties of these elementary particles, and they are different from those quantum numbers, right? Quantum number word simply means address, quantum address of elementary particle. So while classifying these elementary particle, the one thing that we should keep in mind is the address of quantum address of that elementary particle. Now the first quantum number that come is a baryon number, right? Baryon number, and it is represented as a B. We know very well that baryon is +1 for all the baryons, right? Baryons particle, they are nucleons and hyperons. So if the particle is nucleon or hyperon, B is taken as a +1. But if it is antiparticle of that baryon, then it is taken as a -1. So baryon number is simply assigned to the baryons. Similarly, we have a lepton number. Lepton number tell us that the given particle is a lepton, right? It is denoted as L. Again, it is defined only for leptons, these particles, E, mu, tau, and 3 neutrino. So it is +1 for all the leptons and -1 for anti-leptons, right? So this is the second quantum number. Then it comes a isotopic spin or isospin. Now here isospin is a quantum property of elementary particles that we come across in high energy physics, right? I'm not going into the details of isospin because it is a very lengthy topic, but we have to remember that isospin is again a quantum property, right, of elementary particles. And how we calculate it? We calculate elementary particles has two isospins. One is the total isospin, that is denoted as I, and the second is the Z component of isospin, that is written as I3, right, or IZ. So if we want to calculate I, then the method for the calculation of I is 2I plus 1 is equal to multiplicity of the group, right? Multiplicity of a group or a family, right? I mean the number of family members in that group, right? For example, suppose I want to calculate the I for a nucleon family. So 2 members, neutron, proton. So 2I plus 1 is equal to 2. So I is equal to 1 by 2. You can do it, right? So I becomes 1 by 2. Similarly, you can do it for the other families of elementary particles. Now, if I want to calculate the I3, right, then the formula for I3 is Q particle minus Q average. Here Q particle is the charge on the particle, Q average is the charge on the group, right? Now, recall that what I told you in the beginning. We have to remember the exact number of family members in a group, because only then I can calculate the average charge of the group. For example, if I talk about this family, right, 2 family members, average charge is 0 plus 1 divided by 2 means 1 by 2. So if I talk about the I3 for proton, so proton charge is 1 minus 1 by 2. So I3 for proton is 1 by 2. Similarly, I3 for neutron is 1 0 minus 1 by 2. So it is minus 1 by 2, right? Because the charge on a neutron is equal to 0. So in this way, you can calculate the isospin of other families also, right? The next quantum property is strangeness. Now, as far as the strangeness quantum number is concerned, this quantum number is assigned to those particles which are strange in high energy physics or particle physics. So the strange particles are K mesons and hyperons, right? K mesons, you have a K mesons family, where it is? It is, yes, K meson family, and this is hyperons. So K mesons, question can be asked by the examiner. Which of the following particle is strange? So first of all, we have to remember K mesons plus hyperons. these particles are called strange particles, right? These are called strange particles because they do not fit in the theory of other elementary particles. Their behavior is totally different, right? The one thing that is peculiar in this case is they are always produced in pairs. The other thing is they are produced by the strong interaction and decay by weak interaction. So that's why they are called strange particles. So we have to remember k mesons and hyperons, right? K meson family, k plus k naught, and hyperons lambda, sigma, xi, and omega. So these particles are strange. Any other particle of the group, family of elementary particles is not strange. And strangeness quantum number is defined only for strange particles. For other particles, it is 0. Similarly, you can see here the baryon number for the other particle is equal to 0. A lepton number for other particle is equal to 0. It is defined only for leptons. It is for baryons. For other particle, it is 0. Right. Similarly, isospin quantum number is defined for hadrons. Right. Hadrons. For other particles, again it is equal to 0. Right. And strangeness quantum number is defined for strange particle. For other particle, it is equal to 0. Very simple to remember. So now, to find out the value of strangeness quantum number, we have a formula that is q particle is equal to I3 plus S plus B divided by 2. So this is the formula that is given by Gell-Mann and Nishijima. So with the help of this formula, I can calculate the strangeness of any particle, right? Here Q particle is the charge on group, I3 is its Z component of isospin, S is strangeness quantum number, V is virion number divided by 2. So by using this formula, I can calculate the strangeness of different elementary particles, right? For example, suppose I want to calculate the strangeness of omega negative. Then if we calculate the strangeness of the omega negative, it is a very prominent particle. Then when we will calculate it, you can see that it comes out to be -3, right? You can see by calculating it, putting all the values here. For example, in omega negative, Q particle is -1, I3. If I go to the I3 Z component of isospin, I can use that value directly from the table. It is I3 will be, in this case, I can calculate Q particle minus Q average. So Q particle is negative, Q average is -1, right? So it is -2. So obviously it is -2 plus S strangeness plus baryon number. I think it is virion, right, divided by 2. So when I simplify it, it becomes, when I took it to this side, it becomes 1 is equal to S plus 1 divided by 2, right? So let me check it first. The isospin Q particle minus Q average, right? So let me check it. So actually I have done a mistake here. So we should not do it in a hurry. We have to take the all things into consideration. It was Q particle minus Q average. So Q particle in case of omega negative is obviously -1, but the average charge, it is single particle, so -1 divided by 1, so it is -1. So minus average charge -1, minus plus, so it becomes 0. So I3 is equal to 0 for this omega negative particle. So when I put 0 here instead of -2, this was the mistake. Then I will get, I am going to erase it, right? -1, it is 0 here, is equal to S plus 1 divided by 2. So I got S plus 1 is equal to -2. So I got S is equal to -3. right? So as I told you here, the strangeness of omega negative is -3. So it is usually asked in the examination on that what is the strangeness of omega negative particle, right? Or even they can ask the strangeness of other particles also. So by using this formula, Q particle is equal to I3 plus S plus V divided by 2. We should take the help of this formula, but we can calculate these quantum numbers only if we know the family members of different elementary particles, right? And all these things are connected. I3 should be clear, B should be clear. So the next now I am coming to the next quantum number, that is hypercharge, right? Now hypercharge quantum number is again defined to these hadrons, and it is defined as y is equal to S plus B, right? Here S is strangeness and V is a baryon number, right? So by taking the help of this formula, we can calculate the hypercharge of any elementary particle also, right? This is because when why these quantum numbers are important, because these quantum four quantum number, lepton number, baryon number, then isospin, total isospin, Z component of isospin, B, L, I3, right, strangeness and Y. We should know all these quantum numbers very, very clearly. We should be able to calculate these quantum numbers, because in examination you can be simply asked that what is the quantum number of this elementary particle. This is a simple question, but it can be asked that check whether the reaction is allowed or forbidden. So to apply the conservation laws, we should be able to calculate these different quantum numbers, because all the conservation laws are based on the application of these quantum numbers, right? So this is all about some basic properties of high energy physics. I have not gone into the deep details, but I have just covered about the important things of the elementary particles and fundamental forces in nature. In tomorrow's lecture, right, I will cover up some numerical problems, or the problems which are based on these elementary particles particularly, and these questions will be taken from the different competitive exams, and I will solve these questions, right? So thank you very much.